Welcome back to this series of lecture. From today onwards, we will be discussing about the Fourier transform on R. Earlier we have discussed with 2 pi periodic functions. So, where we have identified the 2 pi periodic functions as the functions on the circle group T, and then we did Fourier analysis for Zn and finite abelian group G. So, now here we have R. So, as we know what we need, the first thing is that the concept of the integration on to do Fourier analysis. So, this is Fourier transform on R. So, we know the meaning of minus infinity to infinity f of x dx in the sense of improper integral. And here there is a little departure from what originally we have discussed on a bounded interval. There every continuous bounded function, they are integrable, but in this case you can see that if f of x, this is equal to constant function 1, then you look at minus n to n, then this is f of x dx, this is equal to 2 n, and which goes to infinity as n goes to infinity. So, therefore, it is not Riemann integrable in the from on R. Even if we give some amount of the decay, because this is a flat function. Now, if we want to give a decay, let us say, let us take if f of x is equal to 1 by 1 plus mod x, then if in that case also, if we look at f of x dx, so this is equal to 2 times 0 to n 1 over 1 plus x dx, which is equal to 2 times ln 1 plus x and 0 to n, which is twice ln of 1 plus n, which again goes to infinity. So, even if we have continuous function with certain amount of decay, it may not be integrable over all R. However, if we give a little more decay, if f of x is equal to 1 by 1 plus x square, so then integral minus n to n f of x dx, this is equal to, of course, this is 2 times 0 to n dx by 1 plus x square, and which is equal to 2 times tan inverse of x 0 to n, and which goes to 2 into pi by 2, which is equal to pi. So, now what we see is that if we give little moderate decay of 1 over x square kind of thing, then this is going to be integrable. So, we say that f has moderate decay if there exists a constant a such that mod of f of x is less or equal to some constant times 1 by a by 1 plus x square. Now, if it has a moderate decay and if we take let us say we will assume, because for we will be doing Fourier analysis not for the most general class which are integrable on R, but a subclass of this. So, for our purpose we can assume f to be a continuous function. Okay, so, now if f has moderate decay, then what we want to see is that let us define I n is equal to minus n to n f of x dx. So, now we would like to see that whether this integral I n converges or not. So, as one can see that if I have I m minus of I n, then this is lesser equal to a times integral. Now, suppose if you are choosing m is greater than n, then this is n lesser equal to mod x lesser equal to m, and then this is dx by 1 plus x square. So, this is lesser equal to some constant times a by n square into 2 m minus 2 n, and this of course, is goes to 0 as n goes to infinity. So, therefore, this I m being a Cauchy sequence converges in R. Even we can okay. So, then this is for f was from R to R. Now, just to fix our notation, if f is from R to C, then we can define the integral minus infinity to infinity f of x dx in the form of f is equal to real of f plus I times imaginary of f. Now, if both the real and the imaginary part is integrable in our sense, then we say that even the complex valued function f is integrable. Okay, so, so easily as we have seen earlier, we can derive it integral a f plus b g is equal to a times integral of f plus b times integral of g. Now, there are few operations which are fundamental in R. That means, in R we can translate, then we can dilate it by a positive real number, and then there is a reflection. So, these three fundamental operations, let us call it translation. This is equal to tau y of f at x, this is equal to f of x minus of y, and then this is dilation. You take delta greater than 0 and we define d delta f of x, which is equal to delta times f of delta x, and then reflection r f at x, this is equal to f of minus of x. Okay, so, how does this integral behave with this? Now, if we look at minus n to n tau y f x dx, this just by the change of variable, this is going to so where does it converge? So, this I can write this as minus n. So, let us write one more step, which is equal to minus of n minus of y, n minus of y and f of x dx. So, by making a change of variable, this is what we have got. Now, we are assuming f has moderate decay. Now, we would like to show that so then this minus n minus of y, n minus of y f of x dx minus integral f of x dx. So, this is equal to, I will go from, let us say if y is positive, then I will go from minus n minus of y to minus of n, that will remain f of x dx plus n minus y to n f of x dx. Now, if we take the modulus and if we push the modulus inside, then all these are dominated by 1 plus. So, this is lesser equal to minus n minus of y minus of n mod of f of x and plus n minus of y n mod of f of x, and this is lesser equal to, you can show it very clearly that all these are dominated by 1 by 1 plus x square. So, therefore, if we put that, then this is the length of this interval is yes. So, now in the denominator you have 1 over n square is in the denominator. So, this goes to 0 as n goes to infinity. So, therefore, what we can write is minus infinity to infinity f of x dx. Okay. So, similarly, one can easily show that this is minus infinity to infinity d delta f of x dx. This is nothing but minus infinity to infinity f of x dx. And so, integral over minus infinity to infinity f of minus f r f of x dx, which is equal to minus infinity to infinity f of minus of x of dx, which is equal to, if we write x going to minus of x, then this is again. Okay. So, however, there is one subtle fundamental property of this translation. So, this I would like to highlight. If f is continuous and has moderate decay, then integral minus infinity to infinity mod of tau y f of x minus of f of x dx, this goes to 0 as y approaches to 0. So, now f is continuous, therefore, on if I am looking at, so essentially one would like to look at this f continuous, therefore, on minus n to n f is uniformly continuous. Therefore, for every epsilon positive, there exists a delta which depends only on epsilon. It does not depend on x, such that mod of tau y f x minus f of x, this is less than epsilon whenever mod y is less than delta. That is the definition of the uniform continuity. Therefore, now this in other words, what we can say is that the supremum f of x is less than epsilon. So, now if I am looking at minus infinity to infinity, f of x minus of y minus of f of x mod dx, then this is I can write at minus n to n mod of f of x minus y minus of f x dx plus integral mod x greater or equal to n mod of x minus y minus f of x dx. Now, if f, as we have seen, if f is integrable, tau y f is also integrable. Therefore, this tail of the series, because I n converges to 0, therefore, the tail is going to be small. So, this part is small, let us call this as I can find a n, we can find a n such that integral mod of x greater than n is less than epsilon. So, now this part is less than epsilon, and the other part, as you can see that if f is continuous, if f is continuous, it is uniformly continuous. So, I can pull out with, because this, if mod y is less than delta, then this one is less than epsilon by into 2 n, and then this is epsilon. So, now I can choose my epsilon here, I can take 2 n. So, even if I divided it by 2 n, then this is 2 epsilon, which is small, that is what we wanted, that limit y goes to 0, this tau f of x minus of y minus of f of x, this is less than epsilon. So, that means, this goes to 0 as y goes to 0. Okay, so, this is good enough for us. We will take out some of the properties whenever it is needed for Riemann integration as the course progress. So, for the time being, let us just convince ourselves that these are the basic properties of the improper integral. So, now this after a function being integrable, then the next thing to do the Fourier analysis, what we have seen in the circle case, we needed e to the power I n theta, and in finite abelian group we saw that it is the characters. So, what are the characters? So, now let us recall G from T in finite abelian group, gamma of x plus y, this is equal to gamma x gamma y, that is the character for finite abelian group. And from the circle, gamma from this is gamma of theta, this is equal to e to the power I n theta, which is nothing but its a gamma is continuous and gamma of this one theta plus psi, that is sum modulo 2 pi, this is equal to gamma of theta gamma of psi. So, it is essentially a complex homomorphism. So, this I can put it as a theta as the group operation theta dot psi is essentially theta plus psi sum modulo 2 pi. So, this is a homomorphism, and not only that, it is a continuous homomorphism. So, the first thing one would like to see, let phi from R to circle be a continuous homomorphism. What does that mean? That means phi of x plus y, this is equal to phi x into phi y, and mod of phi x, this is equal to 1 for all x y belongs to R and phi is continuous. Therefore, so now we would like to see the how such maps from R to T which are continuous and homomorphism they will look like. So, okay, so from here one thing we can observe that phi of 0, this is equal to phi of 0 plus 0, which is equal to phi 0 into phi 0, which is equal to phi 0 square. So, this implies that phi 0 is equal to 0 or 1, and because phi is a map to the unit circle, therefore, phi 0 cannot be 0. So, this will imply that phi of 0 is equal to 1. And then what one would like to take, let phi of 1 is equal to alpha, such that mod alpha is equal to 1. Then if I take n a positive integer, then phi of n, this is equal to phi of 1 plus 1 plus 1 n times. So, this is nothing but phi of 1 into phi of 1 into phi of 1 n times, which is equal to phi 1 to the power n, where phi 1 is some number on circle. So, then we would like to see that what happens of if x belongs to Q, then phi of we would like to find what is the value of phi of x. So, phi of x equal x is in Q means x is equal to p by q. Therefore, P is equal to Q times P by Q. So, phi of P, this is equal to phi of Q into P by Q. That means, this is Q is a non-negative integer. Therefore, this is going to be the product of P by Q, phi of P by Q, phi of P by Q, Q times, which is equal to phi of P by Q to the power Q. Now, phi P is an integer, non-negative integer. Therefore, this is nothing but what we have observed earlier is to the power P. Therefore, phi of P by Q is equal to alpha to the power P by Q, where alpha is phi of 1. So, then because now till now we have not used any properties of phi being a continuous function, because phi is continuous. So, now let x belongs to R. So, there exists a sequence of rationals such that x n converges to x. This implies that phi of x is equal to limit n phi of x n, which is equal to limit n alpha times alpha to the power x n, and which is nothing but alpha to the power x, and alpha is mod 1. Therefore, we get that we have phi of x is equal to e to the power 2 pi I xi times x for some xi belongs to R. So, every continuous homomorphism from R to T will look like this, and this is a continuous homomorphism for a fixed xi. So, therefore, now we have the building blocks which are the characters of R, then we will do Fourier analysis in the next lecture. Thank you.